Thank you guys for coming. First of all, I want to apologize about my sound. This sounds a little bit weird. I'm still recovering from a cold. My name is Zhang. I lead the driving safety data science team at Uber. My team works on data science solutions to improve safety on the Uber platform. I'm very glad to be here today to represent the team to talk about telematics data, how to use machine learning, in particular deep learning, to mine telematics data, and how to use Spark to accelerate the development of machine learning models on big data. Before I dive into the details, I want to give you guys a quick overview of the safety team, as well as some of the products that we have built. So when we started the year of 2018, our CEO, Dara, announced that the top priority of the company is to stand for safety. So throughout the years, we have the clear mission to make Uber the leader in safety and also make Uber the safest transportation platform on the planet. So we have made a great progress along that effort, built and launched a multitude of safety products. Here are some examples of the driving safety products we have built. In order to reduce drowsy driving, we have introduced driving hour limits, which puts on a limit on how long the driver can drive on the platform before taking a break. And in order to reduce speeding-related violations or speeding-related crashes, we introduced the speed limit alert, which helps the driver to keep track of the traveling speed, as well as the posted speed limits. And lastly, Ride Check, which aims to automatically detect the potential crashes that have occurred on the platform so that our safety response team can proactively reach out to drivers and riders to make sure they get all the help they need. So all these products are powered by solutions built on top of telematics data. So what is telematics? It refers to a service that uses telecommunication to transfer data collected from sensors in smart things, for example, vehicles or smart buildings. So it falls into the general field of Internet of Things. Our primary focus here is vehicle telematics, which concerns the use of sensor data to understand how, when, and where the vehicle operates on the road. There are generally two solutions to enable vehicle telematics. One is to install sensors onto the vehicle, for example, some dongle devices or LiDAR system used on self-driving cars. However, this is generally a very expensive and not a scalable solution. A second solution is to use smartphones, which has lots of built-in sensors and offer very convenient ways for wireless data transfer. So compared to, and when the smartphone is fixed to the vehicle, for example, through a phone mount, the sensor data from the smartphone can be used to understand vehicle movements. So compared to vehicle sensors, smartphones are widely available. They are relatively cheap, and they have a short upgrade cycle. However, on the other hand, the sensors in smartphones generally have a lower quality compared to the vehicle sensors. And they only measure the motion of the phones compared to the motion of the vehicles. One of the challenges is that the sensor reading from the phones depend on how the phone is oriented relative to the vehicle. A slight change of the orientation may give you very different readings. And if the phone is not mounted to the vehicle, then it's very challenging to use that data to understand the vehicle movements. So the topic of today is going to be focused on smartphone-based solutions. There are two types of sensor data we commonly use for telematics analysis. One is GPS, which provides the absolute location, velocity, and the time of the device. It's generally collected at a low frequency, for example, 0.5 hertz or 1 hertz. That means one data point every second or every 2 seconds. The second type is called IMU, which stands for Inertial Movement Unit, which measures the relative motion of the phone. It has an accelerometer unit, which measures the three-dimensional linear acceleration of the phone. and sometimes a gyroscope unit, which measures the three-dimensional angular velocity of the phone. Compared to the GPS data, it's collected at a much higher frequency, for example, 25 hertz, meaning 25 data points per second. The plot on the right shows some sample readings from GPS speed, the 3-axis from IMU accelerometer, the 3-axis from IMU gyroscope. So as we have seen that sensor data are very rich, high frequency, but also noisy. So how do we mine such data set? In our experience, we have found that the use of deep learning can have lots of advantages here compared to traditional machine learning methods. This is because processing and understanding signal patterns from telematics data can be very challenging. First, signal data also often have very complex and diverse patterns. Here, the plot shows the accelerometer readings from one of my morning commute trips, where I started driving to the bar station, and I stopped at a red light, checked my email, which corresponds to the section of phone handling. And then after arriving at the bar station, I parked my car and then walked to the train, and then finally got on the train, which took me to the office. So as you can see that this is a very simple trip, but it still has several different activities, which some of these have very distinct patterns compared to the rest. But some of these have minor differences. For example, if you look into the driving part, it's very hard to tell which part corresponds to a harsh brake, which part corresponds to me stopping there, and which part corresponds to a left turn or right turn or U-turn, right? So understanding the patterns there through building features manually is a very challenging task. Second, sensor data are time series, and they are dynamic over time by nature. The dependency over time is very important for building a good prediction model, and such dependency must be accounted for when you build a prediction model. It's not as easy to do this using traditional machine learning methods such as tree-based method, but it's very easy to do using neural networks such as RNN. Here's a second illustrating example where I plotted 15 trips. I'm showing the accelerometer readings here. If I tell you that the first row, the first 5 trips, all have crashes, while the rest do not, how would you go about create some features manually to summarize the difference between these two groups? It's actually not straightforward, at least by just looking at those plots. It's in general very challenging to create features that are very predictive other than some very, very obvious patterns. So deep learning in this context offers a very efficient way to create features automatically that can best summarize the sensor information most relevant to an event of interest. So there are two types of machine learning prediction problems in the context of telematics. One is sequence classification. We have an input sequence from the sensor data, and we want to classify the sequence into some event. For example, is there a crash here? Is there certain driving events, for example, U-turns, brakes? Are there any phone handling events during this period, etc.? So this is basically a many-to-one problem. A second type of problem is sequence-to-sequence prediction. Here we have an input sequence. We also want to generate an output sequence, which could be of the same length or sometimes of a different length. So this is basically a many-to-many problem. One good application here is to align the phone sensor data to the vehicle sensor data so that we can use the sensor data to make inference of the vehicle movements. This is one of the most challenging tasks when you use phone sensor data for understanding vehicle movements. But if we have both the input phone sensor data and also the ground truth vehicle sensor data, then we can use deep learning and sequence-to-sequence prediction to figure out what's the best transformation needed to be applied to the phone sensor data and align that to the vehicle frame. Second example here is also related to sequence classification. So in addition to answer the question whether there's such event, we want to also pinpoint where such an event has occurred. In that case, we can create an output sequence where in the interval containing the event, we code as 0 and we code as 1 and 0 otherwise. To create this output sequence and use sequence-to-sequence prediction to detect where such events have happened. And in applying deep learning in telematics, it is also very important to make good design choices there. This is because sensor data are of high frequency. And if you think about a trip that is 10 minutes, and if you look at all the data points there, you could end up with a very long time series with more than 10,000 of timestamps there. It's almost impossible to build RNN on top of such a large sequence. So one way to do that is to apply some pre-filtering. For example, if there are certain specific events you are interested at, for example, I want to identify events only at the end of the trip, then I can only include a window around the trip end and ignore the rest of the trip. But in general, what we do is divide the long sequence into smaller windows, and each of the windows is small enough for us to apply neural networks. And here is example architecture for window level for sequence classification. At the bottom layer, we have the raw data. We can feed the data directly into the neural network, but sometimes it's beneficial to do some further feature extraction and feed that extracted feature into the neural network. And in the neural network layer, we often have LSTM or GRU, multi-layer LSTM. Because this is a sequence classification, our label is on the whole window level. So we only take the hidden state from the last layer at the last time step and then link that to the label. We often refer this to our sensor embedding that can be used across multiple problems. So on the feature extraction part, one way to do that is to extract some very basic sample summary. For example, for each time series, you compute the minimum, the maximum, the mean, the standard deviation, etc., as well as some frequency domain features such as fast Fourier transform coefficients. And then you can calculate them. You do that for all the time series to get input vector to fit into LSTM. Second type is just to apply a one-dimensional CNN with the filtering, pooling, etc. You can build multiple layers there and get the last layer and use that as input to the LSTM model. So one unique characteristic of the sensor data from phones, as I mentioned, is that the sensor readings depend on how the phone is oriented relative to the vehicle. A slight change of the orientation will result in very different readings. Take this figure as example. Suppose we rotate the phone twice, 45-degree clockwise, 90-degree clockwise. Even though the underlying vehicle has not moved, the sensor readings are very different now. This is very challenging when we use phone sensor data to understand the vehicle telematics. But when building deep learning models, actually we can leverage this property because we can create artificial data by rotating the phones and use that artificial data to augment your training data set. And with that, we can create a new sensor readings, but the label stays the same. And enlarge the training and the validation data set to build more robust models to different phone placement angles. So in the model development pipeline, we have two versions. One is for the non-deep learning version. We have the data starting in Hive, and we do some feature engineering in Spark, and also train the model in Spark using Spark ML. and oftentimes XGBoost, all within Spark. Oftentimes we include the millions of trips in the training and also millions of trips in the validation. After iterations of the model, we've saved the whole model pipeline, which we can load directly into another Spark session to score new trips. On the deep learning side, it follows a similar pipeline. We have the sensor data starting in Hive, and then we do some basic feature engineering in Spark, and then we train the model in TensorFlow, and then save the model which can be loaded into another Spark session to create the sensor embedding, which we can feed into existing XGBoost model, or we can use that as a standalone model. So I want to highlight some of the tools that have been developed and open sourced by Uber in the deep learning space. One is Hereward, which allowed distributed training of deep learning models across multiple machines to handle very big data. This is very important for our context because telematics often involves huge volumes of data. So Hereward supports training in TensorFlow, Keras, PyTorch, and it can be easily installed, and it's very easy to change the existing code to leverage this feature. A second tool is Pedestal that has been developed by the Uber ATG team. There's no native support of a Parquet data file in the popular machine learning, deep learning packages, at least in the early versions. So one has to convert such Parquet data files into some other data formats that can be loaded into TensorFlow or PyTorch. With Pedestal, one can actually load Parquet data directly into the deep learning packages, avoiding such intermediate step. So across many telematics applications, we have found that the use of deep learning models perform significantly better than traditional, than standard machine learning models. I believe that telematics, the use of deep learning in telematics can bring in lots of value. And on the other hand, because some of the unique challenges in telematics, for example, you have to deal with huge volumes of data, you have to handle the complex and diverse patterns from signal data. It also has lots of opportunities for innovation to get better deep learning models to improve the performance, as well as new methods to improve efficiency for data transformation and the model training pipelines. So this is a very exciting area that we are investing more into. I think this is all the material I want to cover today. Thank you all for attending, and I welcome any questions from the audience.
Yeah, hey, I just have a quick question. So you talked about using deep learning for this. And one of the things was determining whether or not like a crash has actually occurred. I would guess that most of the time and most of your data sets are actually non-crashes. So I would presume you have just a small data set that's actually labeled as crashes. How are you actually dealing with that, considering that a deep learning model has so many parameters that like how are you actually teasing out that signal when maybe like 99% or even more of your data set's probably not a crash?
So yeah, that's a great question. So I think this is the general problem of modeling rare events. There are some standard methods, for example, oversampling the positive labels or downsampling the negative labels. We have tried methods like that. But what we found actually is in that case, including more negative labels is also very helpful because they can help you to tease out the false positives. So in our applications, we actually didn't do lots of the downsampling. We include lots of the negative labels and ask the model to figure out.
Hi. Well, thank you for your talk. I have a couple of questions. So one of them is, in this case, you're talking about analyzing the accelerometer, right? And this is like a long stream of data, you have said. Do you usually, like in Uber, when you want to analyze this data, do you collect all of it, or do you collect like samples of it, or do you run some sort of all these, once the models are trained, do you run them in the phone?
So is your question regarding whether we sample certain data when building the model?
Like, yeah, because the accelerometer, right, it could be running all the time. So I guess this might raise the battery consumption of the phone if you keep sampling. So my question is, do you usually like sample all this data and put it into the Uber's database, or do you like run all the models that you have trained on the phone to like classify it, for example, for the crashes or turning the vehicle and all this kind of thing?
So on the data collection part, I don't know the details. I think it's more of an infer question. But when training the model, as I mentioned, we do feature extraction. So instead of using the very raw data, which let's see, is collected at over 20 hertz. If you have more than 20 data collections per second, we often do additional feature extraction to summarize the data. For example, you can just compute the sample stats and use that to feed into your neural networks. First, you can reduce the noise from the raw data. Second, you can reduce the time steps without losing tons of information there. We have found that it's actually beneficial to do some data summary before feeding into the model.
Okay. Okay, thank you. And the second question is more regarding on how you choose these windows in which you partition your data, right? Yeah. Because many times, I guess, it could happen that you cut, like, and you have two things on the same window.
Yeah, that's a great point. I think it depends on the problem. Some problems like, you want to predict a second level event, and each window is independent. So you can, create windows that do not have overlapping, are not overlapping. And sometimes, if you want to capture events that could occur in a longer window, you could create windows like sliding windows with overlapping, or you could, build one layer on top of the small window and then another layer kind of on the window level to capture kind of the whole, the dependency over a longer time period.
Okay. Okay, thank you.
Yeah.
It's kind of a simpler question, but I just want to make sure that I understand, or just more like clarifying. So I assume for like crash detection, you're getting your labels from your customers. Did you just get into a crash? And that's probably the main source of labeling there. And then for things like hard braking, is that unsupervised, or are you getting how are you, or is it supervised, and where are you getting your labels from?
So, that's actually a great question. Collecting ground truth data is very challenging. So we have different ways of doing that. One is, okay, you just build an app and then you collect the data going to the field. Define, okay, what are you trying to do? For example, if I want to build a phone handling model, I can build an app and then I go out to drive and handling the phone, right? You collect, enough data and build data on top of that. That's one way to do that, but the risk of that is like you are gonna fit your model into probably certain scenarios, right? That is not very representative of the real world. The other thing is like, if you have some kind of sensors installed on the vehicle, you can apply some basic signal processing on those sensor data to get the ground truth, right? If you have a very high quality GPS, you probably just by processing the GPS, use some simple logic, you can get the ground truth. And then if you also have the phone sensor data, then you can now use kind of the vehicle sensor as your ground truth and the phone sensor data as your input and build the model.
So is that what you use live? Is that's your sense of ground truth? Actually using sensor or actually using data from the vehicle?
I don't think we have that.
Right. Yeah.
No.
So.
Yeah, I'm saying like it's probably just like offline. If you can build a fleet of vehicles that have vehicle sensors installed, right? To collect those things yourself,
Okay,
right?
fair enough. Thank you.
Great talk, thank you. So I was curious, you mentioned some performance graphs at the end, and you mentioned that the standard machine learning models didn't perform as well as deep learning for this telematics kind of data. What's your intuition as to why, deep learning, it's a good fit for this kind of context?
Yeah. I think with the standard machine learning methods, you have to create the features manually, right? You have to define, okay, what are the features you want to extract from the sensor data, and then you feed that into, let's see, the tree-based machine learning algorithm. It is, I have two illustrating examples there. It's very hard to create the features there, right? By just looking at the data. So it generally takes a lot of time. Second, some of the patterns are very subtle. Even just by looking at the data, it's really hard to summarize, okay, what's the best way to summarize them? With deep learning, it kind of automatically figures out what's the best way, what's the best transformation to summarize the sensor information that is most relevant to kind of your prediction event. So I think the intuition is basically, it has better and more automatic feature engineering compared to, build the features manually yourself and then test it in another model. Does that make sense?
Thank you.
Okay.
Thanks, lovely talk. I was wondering if you have a sense of what features are being learnt by the RNN, and also if you have, presumably it's fast stops, right? And if you're able to distinguish between someone braking suddenly at a light, for example, compared to an impact in a crash. That's
Yeah.
two separate.
Yeah, definitely. You can definitely plot the kind of the hidden layers to see like roughly what's the meaning of that. There's definitely information about okay, how fast the car is driving, is there a sudden brake, are there kind of high forces, etc. But since this is kind of a black box, you really can't tell this is exactly that. But the best you can do is kind of try to understand what it is capturing. Does it make sense?
Do you find something that's able to distinguish between real crashes and other things that we would be tricked by, like sudden braking at a light?
Well, I think it can do a very good job on certain things. For example, one of the false positives we run into is if a phone falls off the phone mount, then standard ML model, if you build a feature that captures such movement, it's more like a harsh brake or big force, then it will treat it as kind of a potential crash. But with deep learning model, if you look at a kind of a longer window before and after, that actually can mitigate the issue there.
Hi, good presentation, thank you. Quick question, going back to the earlier question the gentleman was asking is, along with the data that you get, are you also complementing that with data from the vehicles themselves, like their onboard diagnostics, or working with the vehicle manufacturers?
So I'm not aware of any effort there, like working with the manufacturers. But I think it's mostly related to ground truth data collection. I think the collection of both phone sensor data as well as vehicle sensor data allows us to get some ground truth and build kind of learning models on top of that.
So the vehicle sensor data is coming from, not from the application, not from the Uber app. It's, what is the source of the vehicle sensor data?
So there's different types. There's the OBD2 the stuff.
Okay,
there's the the kind of there's also kind of better sensors, high quality sensors, which you can attach to the vehicle, right? So versus a phone, you put it on the phone mount that vibrates, has a lot of the motion from the phone itself, or higher quality GPS, high frequency GPS. That will just there's really no ground truth there in some sense. It's just like which one has better quality. We know that phone sensor has probably the lowest quality, has the most issues, but that's the most scalable solution, right? How can we improve it using benchmarking it with better quality sensors? So how can we build algorithms to kind of transform the phone sensor to higher quality? Kind of that's the question to answer there.
Yep, thank you.
Just
thank you all for coming and making Spark Summit such a great event. Big round of applause once more for Wayne Zhang. Have a great rest of your day, guys, and enjoy the weekend. Thank you.